lightning is produced? Lightning can be produced between opposite charges within a cloud, between two or more separate clouds, or between the cloud and the ground. It is associated with very strong electric fields in the atmosphere. Many scientists are still studying the process behind its formation. However, they have arrived at a possible explanation. As the water particles move upwards in the clouds, they interact with the other particles, such as hail and ice crystals. Their collisions make the water particles to be positively charged, and the particles which move downward become negatively charged. Because of this, the bottom part of the clouds become negatively charged, which will induce positive charges on the ground. The negative charges which were deposited at the clouds will be discharged to the ground in the form of lightning. The formation of lightning is quite fascinating, but a good thing to know about it is how these electric charges in the clouds interact with the charges at the ground, even without touching. In this lesson, we will be able to understand how charges can affect each other even if they are not in contact. From our previous discussion, we were able to know that the electrostatic force is the force that acts between two charged particles. This force, which sometimes we call Coulomb force, can be either attractive or repulsive, depending on the charges which are interacting. This characteristic of electrostatic force is what makes it different from other forces, say gravitational force. Can you recognize their main difference? That is correct. Gravitational force is always attractive. Throughout our discussion of general physics, we have been introduced to two field forces, electrostatic and gravitational. Both electrostatic and gravitational force act between objects even if they are not in contact. An electric field is defined as the amount of electric force on a charged body exerted by external charged bodies. For us to visualize this definition and how electric force exists between two particles, let us consider two charges. Let us label them A and B. Let us say the charge A has a very large charge compared to charge B. Because of the charge that B carries, it alters the properties of space around it, producing a reactive force with charge A, which also alters the properties of its surrounding. Again, since both of them are charged particles, they experience repulsive forces with one another. By putting this process in mind, we will be able to understand how a charged particle interacts with another charged particle. To elaborate further, let us consider a body A as sole charge in its space. Let us remove our example charge B and instead label its former position as P. Even if there is no charge at position P, charge A can still alter its environment because it produces its own electric field. This electric field can exist radially from A. When we say to exist radially, what do you think does it mean? Correct. The electric field exists all around A. I hope we can establish at this point that a charged particle produces an electric field around it. And when another charged particle is present, it reacts to it by experiencing an electric force. In general, we can then formally define the electric field at a point P as the electric force acting on a charge, which we conveniently call a test charge, placed at that point per unit charge. In this definition, we can deduce the relationship between the electric field and electric force. The electric field due to the source charge at a location of a test charge is the electric force on the test charge per unit charge. Mathematically, it is represented as where E is the electric field, F sub E is the force between the charge and the test charge, and Q sub 0 will be our test charge. The SI unit of our electric field will be Newton per Coulomb. From the mathematical definition, we can define electric field from the equation of the Coulomb's law. Can you recall which of the following formula is the correct Coulomb's law? It seems that you really are reviewing your lessons. With this equation, we can alter this to match our definition of the variables that we have. Q sub 1 in our Coulomb's law will be our Q, and Q sub 2 will be replaced by our test charge, Q sub 0, making our equation to be like this. When we plug from our previous equation, our new equation will be, algebraically, we can reduce this equation as E is equal to K times absolute value of Q all over R square, where E is the electric field, Q is the charge that creates that field, R is the distance between Q and the test charge, and K is the Coulomb's constant with a value of 9 times 10 raised to 9 Newton meter square over C square. Very briefly, let us have example problem using this equation. I have reserved other problems for our sync session. Here, it says to find the magnitude of the field at 2 meters from a 2.0 nanocoulomb charge. The charge and distance of the point from the charge are given in this problem. We are asked to calculate the electric field 2 meters away from the charge. We will use our derived working equation. After we made sure that all variables are available in our computation and are expressed in proper units, we can substitute this now in our equation. We have here the Coulomb's constant multiplied by 2 times 10 raised to negative 9 coulombs. Since we need to express this in coulomb, all over 2 meters square. Cancel the units, and what will be left is Newton per coulomb, which is a standard unit for electric field. Simply input this in your calculator and your final answer will be 4.5 newtons over coulomb. And that is the electric field at 2 meters away from the charge. In the next lecture, we will represent the existence of electric field. Your knowledge on vectors from previous lessons will become very useful as we draw them. But that is all for this lecture. This is Gilmar De Castro, and see you in the next video.